Morning, afternoon, evening, whatever it is, when you happen to access this file, this is going to be your video for the example problems of chapter 6. There are quite a few of them, but they're mostly short and sweet. So let's begin. Lifting a water bottle, a 1 liter bottle of water has a mass of 1 kilogram. To understand the magnitude of a joule, determine the distance you must lift a 1 liter bottle of water at constant speed in order to do 1 joule of work. All right. Your force equals gravity, weight, mg, and your work is equal to force FD cos theta. So your work is going to be equal to mg d cos 180, because you're lifting it. Oh, cos 180. It's going to be negative work. So it's going to be, let's see, work is 1 joule and divided by, it's just negative work. So just know that. That's not going to change the magnitude of it at all. So 1 kg times 9.8 meters per second squared equals 0.1 meter. All right, so a joule is a pretty small unit as far as it goes. All right, now 6.2. These people each, 3 people each apply a constant force of 200 newtons horizontally on a car that has run out of gas. To understand the magnitude of a joule, again, determine the work done on the car by the 3 people to move it 5 meters. All right, so which just not direction, we're just going to determine magnitude. So work equals force times distance. So we have 3 people. Wait. Yeah, we need to determine the work. 3 people times what was the force? 200 newtons. 200 newtons times 5 meters. And that's going to be equal to 3,000 joules. So once again, a joule is kind of a small, relatively small unit as far as it goes. All right. Doesn't take much to get it, not too much work done in a joule, in other words. All right, 6.3. 6.3 reads. Well, you might want to do math box 6.1. I'm looking at it now. Dot product. It's good stuff. Okay. Yeah, dot product. That's what we're doing when we do the work, and work is a scalar. Okay, anyway. Let's see. 6.3. Each Earth exerts a gravitational force on the moon of 2 times 10 to the 20 newtons. Treat the orbit as a circle of radius 3.8 times 10 to the 8th meters and determine the work that Earth does on the moon. Okay, so work is FD cos theta. And it's FD cos 90, so that's going to be a whole 0. So work does, so equals 0. So Earth does no work on the moon because it's the direction of the force is perpendicular to the direction of motion. 6.4. In executing a dive from the 3-meter springboard, a 600 kg diver passes the board on the way down at a speed of 8 meters per second and enters the water at 11 meters per second. How much work does gravity do on the diver from the moment she passes the board on the way down until she hits the water? Neglect air resistance. All righty. So we have work equals FD. And then we're going to do work energy theorem. So equals delta EK, change in energy. So equals 1/2 M V final squared minus V initial squared. So equals 1/2 times 1/2 times 60 kgs times 11 meters per second quantity squared minus 8 meters per second quantity squared. And that's all going to be 1.7 times 10 to the 3rd joules. All right. And that's work done by gravity during that distance. All right. Does it say what the distance is? All right. Is that right? Let's go with the 60 kgs times 9.8 meters per second squared times, what was that? Did they say 3 meters? 3 meters. Let's just verify on clear 60 times 9.8 times 3. I get the same answer. So there you go. So physics, I get 1764. I did the force times distance here. Yeah, you do either way. They don't do it in your book that way, but interesting. Okay. Or do they do it in your, no, they don't. They just do the delta EK. I just did the height of the diving board times gravity times the mass of the diver. All righty. So you do it either way you want. Many ways to get to Rome here. All roads lead to Rome. Awesome. 6-5. All right, what does it tell us here? 6-5. The U.S. National Highway Transportation and Safety Administration. Oh, I think I'm going to skip this. Or did I? Wait. No, I didn't. There was one that I skipped. Yeah, I guess this is fine. Lists the minimum braking distance for a car traveling at 20 miles per hour, about 8.9 meters per second, to be 25 feet or 7.6 meters. What is the deceleration required to stop the car in that distance, assuming the brake force is constant? For the minimum distance to stop, assume that the wheels of the car have stopped rotating, so the kinetic energy between the tires and the road result in the work necessary to reduce the friction. So I guess we're skidding there, huh? All right. Okay, so work equals FD cos theta equals negative FD, because we're going equals delta EK equals 1/2 M V final squared minus V initial squared. All right, and this is 0. So we have a negative FD equals negative 1/2 M V initial squared. All right, so I'm going to take these negatives out. So we have FD. F is F equals MA. MAD equals 1/2 MV initial squared. The M's can go. So acceleration equals V squared over 2D, right? Yeah. All right. And that would be V is, let's go over here, 8.9 meters per second, quantity squared over 2 times 7.6 meters. The answer is 5.2 meters per second squared. That's A. All righty. Okay. I skipped 6.6. I didn't find it that interesting, but you can do it. I mean, it's always good to practice how far to stop. Let's see. Let's go ahead with 6.7. It says actin packs a punch. To fertilize eggs, horseshoe crab's sperm must penetrate two protective layers about 40 micrometers thick. To achieve this, a 60 micrometer long bundle of coiled actin strains out and pushes with a force of 1.9 times 10 to the negative 9 newtons. If the actin bundle has mass on the order of 10 times negative 10 to the negative 16 kilograms, what is the speed of the actin bundle at the end of this process? All right. FD, and remember it starts equals delta EK. So FD equals 1/2 M V final squared minus V initial squared. And this is 0. So FD equals 1/2 M V final squared. We're looking for V final. So V final equals 2FD over M under the radical. Yeah, that's right. Okay, so then you fill in the blanks and you can solve for that. Oh, by the way, yeah, the force is 1.9 times 10 to the negative 9 newtons, and the distance is the distance of that actin. 60 times 10 to the negative 6 meters, which is 60 micrometers. All right, that was 6.7. All right, example 6.8 says, at the start of a race, a 4-man bobsled crew pushes their 210 kilogram sled as fast as they can down the 40-meter straight, relatively flat starting stretch. They apply a net force of 200 newtons aligned with the direction of motion. What is the speed of the sled right before the crew jumps in at the end of the starting stretch? Neglect effects due to friction. So we have a work energy theorem again. Speed, and so they don't want to know the direction. They're just asking for the magnitude. FD equals 1/2 M V squared. We want V. So FD times 2 divided by M under the radical equals V. I don't know the values. You can put them in yourself. It's just like the problem before it, isn't it? I think it is. Sure it is. Exactly the same equation. So good practice doing a bunch of these. Just practice, practice, practice makes perfect. All right. Let's see. Are we going on to 6.9? Yes, we are. But first, before you do that, you might want to read about springs and work by a spring, and the equals negative 1/2 kx squared. Okay, so 6.9, work those muscles. The athlete in figure 6.10 stretches the exercise apparatus 47 centimeters from its unstretched length. The spring constant of the cords is 860 newtons per meter. When you assume the cord acts like one spring, how much work is done due to the athlete? All right. So work equals work for the spring equals 1/2 kx squared. That would be, yeah. Where x is the displacement from work equals 1/2 k. I don't know what was k. 860 newtons per meter. That's the spring constant. Times 0.47 meters quantity squared. Going to be 95 joules, negative 95 joules. Sorry, this is a negative kx squared. Not asking, they're asking for the work, not the negative 95 joules, right? You're going against the grain there. The spring wants to push you out and you're going against it. All right, that was 6-9. Let's see, 6-10. All right, 6-10. All right, where is 6-10? Wow. Okay. Well, read all this stuff. It's good stuff. You throw a ball straight up with an initial speed of 15 meters per second. How high does it go above the point where you release it, and ignore any effects due to air resistance? We're going to use conservation of energy here. We got what gives it energy, what takes it away. So what it gives it energy is that initial bump, the initial velocity, kinetic, 1/2 mv squared. And that's going to, because it's going to have a final velocity of 0, equals mgh. So I don't need these. We want to solve for h, right? Yeah, we do. So h equals v squared over 2g. You can, I'll leave the values to your pleasure. You go ahead and put those in there and solve and have a good time doing that. All right, conservation of energy, trading in kinetic for potential. That's all the energies we've got going on in this. Your book puts a lot on it, but read how they do it. And then if you can simplify it to your pleasure, that would be good. All right. All right, so we are on 612 now. Yeah, go ahead and do 611, but I'm doing 612. 612. All right, here we go. It says, cars on a roller coaster on lunar land. At lunar land experience, wow, we have a theme park on the moon. Experience no air resistance and no friction. A roller coaster car starts from rest at the top of the first big incline, a height of 115 meters above the surface of the moon. What is the car's speed when it reaches its lowest point at the track, which rests on the surface? The acceleration due to gravity on the surface of the moon is g moon equals 1.62 meters per second squared. Now we're doing the opposite thing. We're trading in that potential energy for kinetic. So mgh equals 1/2 mv squared. M's cancel. What are we solving for? Oh, yeah. Speed, right? All right, so v equals the square root of 2gh, and it's not 9.8. Remember, it's that v equals the square root of 2 times 1.62 meters per second squared. And what was h? 115 meters. All right, just conservation of energy one more time. We're trading that potential in for kinetic, and these are conservative forces, so the path is irrelevant. It is independent of path. All right, that was 612. 613. 613 says, a child's toy shoots a marble into a maze with a horizontal spring that has a spring constant of 11 newtons per meter. The marble has a mass of 16 grams. If the spring is compressed 3.4 centimeters and then released, what is the speed of the marble when it leaves the spring? Now we've got that elastic potential energy of the spring. We're trading that in for kinetic energy. So 1/2 kx squared equals 1/2 mv squared. So we're solving for v, right? All right, so I don't need these halves. So let's see. I have V equals the square root of kx squared over m. And that equals the square root of 11 newtons per meter times, you got to convert to meters here. That would be a negative 0.034 meters squared over 0.016 kgs. And you go ahead and solve that. That's 613. So now, once again, it's an energy exchange. We're exchanging that elastic potential energy of the spring for kinetic energy of the marble. So there's no free lunches here on this earth. It's all one thing exchanged for the other. Nothing, you can't create something out of nothing in physics, because if you could, then people would want to study it really hard, right? That would just be magic. All right, so 613. All right. Oops. That was, oh, well, 1 second. I'll find my mouse. Weird. Oh, well, I just have to use the manual. Golly, that is just weird. Just fell on the floor and disappeared. All right, 615. We just did 614, 615. Let's see. 615 reads. Oh, we didn't do 614, or did we? No, we didn't. We're going to do 614 now. A child, oh no, we just did 614, sorry. All right, so 615. United States patent number, whatever it is, adjustable spring rate pogo stick, describes a pogo stick that has a spring mechanism which can be adjusted to accommodate riders of a range of weights. When the spring constant is adjusted to its maximum value of 20,300 newtons per meter, a 100-kilogram kangaroo standing on the pogo stick partially compresses the spring. If the kangaroo jumps on the pogo stick, it compresses the spring an additional of 0.25 meters. If the kangaroo and pogo stick are at a forward angle of 60 from the horizontal, when the spring returns to its equilibrium length, how fast are they moving at that moment? All right, so we have K of the spring equals 20,300 newtons per meter. The mass is 100 kgs. Delta X equals 0.25 meters. Theta equals 60. He's leaning over. All right, so we have this 1/2 kx squared equals mgh. Oh, wait a minute. That's going to be a negative because it's going back up. That's going to take energy to move the kangaroo back up to that original position, plus 1/2 mv squared. So this gives it energy. That takes the energy, and then we'll have energy left over. But this H, it must be noted, is a H equals 0.25 meters sine of 60, right? Because he's leaning, he's not going back up. The height that he's going back up is the vertical height is just that times the sine of the angle. All right. Wow, that really is kind of hard. All right, so I'm glad I found my mouse. All right, so now let's move on. So this gives it the initial push, this takes energy away, and then we have that left. If we even have any of that left, but let's see. Okay, so we have the final. Oh, let me just go ahead and do the derivation. Okay, so 1/2 m v final squared equals 1/2 kx squared minus mg delta x sine theta. Okay, so this is what we have left. This gives it the initial energy, that takes them away, and then we have that left. So let's take these halves out and put a 2 here. And let's take these m's out here and put an m there. Now we have v final squared equals k over m times x squared minus 2g delta x sine theta. All right, and this is delta x as well too. And then we're going to take the square root of both sides. And you could do this and fill in the blanks and solve for the value. Okay, that was 615, I believe. 616. All right, 616 says, a block is given initial speed of 3.8 meters per second on a horizontal surface. The coefficient of kinetic friction mu k between the surface and the block is 0.35. How far does the block move before coming to a stop? Okay, so we have our initial energy is 1/2 mv squared equals fd. F is friction, mg, the normal force, mu k times d. So I don't need my m's. Let's see, we were solving for d, right? V squared over 2g mu k equals d. So once again, I have my initial energy, and we're turning into work. This is the work energy theorem with friction. All right, so practice these problems. They're pretty good. And that's all that I did for this chapter. All right, so we'll see you on the next time.